Okay, I posted a video on my alternator that I turned into a brushless DC motor. That's actually not brushless. I don't have permanent magnets inside, so I'm still using DC power through these wires here to the brushes inside, and that's creating the magnetic field on the rotor. And then I have the three-phase wires from the stator right here, and I have that connected to a three-phase bridge inverter right here, and here's one of the phases, another one, and the last one. And this microcontroller right here, which is an Atmel Mega 32, controls the whole thing. So this blue wire here goes to a Hall effect sensor that's in front of these permanent magnets on this plastic rotor that I made. And there's 36 of them, and each one is turned the other way. So for instance, this one might be N, and the one next to it would be S, and then N and S. And what that enables me to do is on this blue wire I can see which magnet it's on. Is it on an N or an S? So when you spin this, you get a 0 and a 1, as you can see right there on the oscilloscope. Just get zeros and ones, one after another. So my program can tell whenever it switches from a 1 to a 0 or from a 0 to a 1, the microcontroller knows that it's time to go into the next commutation step. So it makes a change on what transistors are turned on the inverter, and then it works, it spins. Getting up to this point, actually getting it working properly, has taken me a bit over 4 months. It's not easy to understand all the different things that actually go into a motor controller like this, and it's still just very crude, very simple, and all connected temporarily. So yeah, and then I have this potentiometer, which I use for controlling my pulse width for the power to the stator, and I have a fixed pulse width controlling the power through this transistor to the rotor's coil. So let me just turn this thing on here and connect up my battery, and you see right here that right now the rotor's coil is taking about 1.9 amps. I'm not sure what the voltage is right now, but it doesn't really matter. So now it's a bit stiffer to turn because there's magnetic poles on the rotor now, and then all you have to do is start turning the potentiometer and give it some more power to the stator, and the microcontroller will start switching the power as needed to the stator to make the motor run. Sometimes it needs a kickstart. It's because there's only one Hall effect sensor. Usually 3 are used. Just gonna hook up this measuring the current, and right now there's current of about 1.6 amps. That's interesting. I think my timing is off a bit. It seems to be running a bit rough. Well, anyway, Whoa, whoa, that has tons of torque. It almost fell off the table. What the heck was that? Oh! One of my wires came off. I was wondering why this thing was going so rough. This wire right here started sparking. That's how I noticed. It was on here with the red wire, one of my phase wires. So its connector's actually underneath the battery. Well, that explains that. Just reconnect that up right there. There we go. There, now it should run a fair bit smoother. Yeah, there we go. That's more like it. So now it's at full speed, and I have a little RPM meter that I made, and I have one magnet in that inner slot, so I can use this Hall effect sensor and get the RPMs. So about 800 RPMs, sometimes slightly more. That's the maximum speed when the timing is set for the most torque, and when it works with the least amount of current, when you don't have any resistance. And right now with this lead-acid battery connected, if I tried to stop it with my hand, when the current gets up to about 35 amps, you can't hold it. And I haven't thus far been able to actually stop it completely. So it has a lot of torque, and I just got a chain and sprockets that I'm going to try to use.